To everyone present, we are Group 11, and I go by the name Justin. And today we will be presenting our work on block diagram reduction in classical control systems. In control systems engineering, block diagrams are used to represent the flow of signals in a system. These diagrams help engineers understand how different components interact to produce an output from a given input. However, complex systems often contain many interconnected blocks, feedback loops, and summing points, making them difficult to analyze directly. That is why we use block diagram reduction techniques, where these techniques allow us to simplify a complicated system into a single equivalent transfer function. And this final transfer function represents the overall behavior of the system and is very useful for analysis, design, and stability evaluation. In our work, this is our work, we were given a block diagram consisting of several forward path gains and feedback elements like this. Our goal was to simplify the system step by step using standard block diagram rules. So throughout this presentation, each member of the group will explain one part of the reduction process, from identifying the structure to applying formulas and arriving at the final transfer function. Let us now begin by looking at the structure of the given system. Thank you.
Okay, I go by the name Ahin, and I'm here to continue from where my colleague left off. The given control system consists of three main forward blocks part, which is G1, labeled G1, G2, G3. These blocks represent different components in the system that process the input signal sequentially. In addition to the forward part, these two feedback elements, there are two feedback elements labeled H2 and H3, which feed part of the output signal back into the system. So this is H3, H2, and then H1. So continuing from where I left off, feedback. Feedback is important because it influences the stability and performance of the system. We also observe summing junctions. These are the summing junctions. These are the summing junctions where signals are added or subtracted, and pick-off point. This is an example of a pick-off point. And pick-off point where a signal is split and sent to another part of the system. Because of these multiple loops and connections, the system is quite complex in its original form. Therefore, we cannot directly write the overall transfer function without first simplifying the diagram. To solve this problem, to solve this question we have here, we apply block diagram reduction rule, which include moving of the pick-off point, combining blocks in series, combining blocks in parallel, eliminating feedback loops. This is an example of a feedback loop. Now let us begin the first step of the simplification process. I'll let my other colleague continue. Thank you.
Okay, so I'm continuing from where my colleague left off. Now, with the block reduction, we have to look out for the place to start and to make this whole thing really easy to simplify. All right. So now looking at the feedback H1 and H2, we will have to move the feedback behind G3 to make the whole loop easier to simplify. Now, okay, so now after moving the pick-off point behind J3 to make the whole block equivalent to the previous one, we divide again J3 by H2 and H1 to make the whole thing equivalent to the previous one. Okay. Okay, so after doing that, you see some of the blocks and parts of the whole block will be clear, and you clearly see the series portions and the feedbacks, the negative and the positive feedbacks in the whole block, making this all easier to work with. All right.
Okay, so I'm going to continue from where my colleague left off. And now in the step 3, we'll be reducing the feedback loop with H3. Now we consider the feedback loop formed by H3 and the combined block J2, J3. To simplify the feedback loop, we use the standard control system formula J over 1 plus GH all in brackets. Now in this case, the forward path is G2, G3 and the feedback path is H3. Applying the formula gives us a reduced block equal to G2, G3 all over 1 plus G2, G3 plus H3. This step eliminates the inner feedback loop and replaces it with a single equivalent block. Reducing feedback loops is one of the most important steps in block diagram reduction because feedback greatly affects system behavior and stability. Now that you have removed this loop, the diagram becomes simpler and easier to continue reducing.
Hi, I'm Albert, and I'll be taking you through step 4. At this stage, we have simplified the inner loop, but the system still contains additional elements, including J1 and feedback H2. We now carefully examine the remaining diagram to identify any further series or feedback relationships. We notice that the reduced block from the previous steps is connected in series with J1, meaning they can be multiplied. We also observe that H2 forms another feedback loop around parts of the system. By applying the same reduction principles again, we continue simplifying step by step until the diagram is reduced to a single forward path with a single feedback expression. This systematic approach ensures that we do not miss any connections and that the final result is mathematically correct. Thank you. Now, we combine G1 with the reduced block obtained earlier. Since they are in series, we multiply them to obtain the new forward path. That is G1 times G2 times G3 divided by 1 plus G2 G3 plus G2 H2. This gives us the expression G1 G2 G3 all divided by 1 plus G2 G3 plus G2 GH. At this point, we have successfully combined all the forward path elements into one single expression. This is a major step because it represents the entire system behavior in a systematic mathematical form. Thank you.
I'm Sasa Emmanuel, and I'll be continuing from where my colleague left off. So, now after completing all the reduction steps, we arrive at the final transfer function of the system, which is G1, G2, G3 over 1 plus G2, G3, H3 plus G2, H2. And now this expression represents the overall relationship between the system input and then the output. It shows how the gains and feedback elements affect the system performance. And with this final transfer function, engineers can now analyze the system for stability, response, design, and improvements of the design. Thank you.
So I'm George Terry, and this is the block diagram. This is a block diagram algebraic, and after the algebraic computation of the block diagram, we got G1, G2, G3 over 1 plus G2, G3, H3 plus G2, H2 plus G1, G2, H1. And we reduce the block to get this final transfer function block, which is the transfer function. So in conclusion, the transfer function of the block diagram using block reduction method is G1, G2, G3 over 1 plus G2, G3, H3 plus G2, H2 plus G1, G2, H1. Thank you.